1128. Right now, somewhere above you, the night sky is lying to you. It has always lied. It lied to the first human who tilted their head back and stared upward from a savanna floor 100,000 years ago. It lied to the Babylonian astronomers who mapped constellations onto clay tablets. It lied to Galileo when he turned his primitive lens toward the heavens and saw moons orbiting Jupiter for the first time. And it is lying to you tonight in this moment, with the same quiet confidence it has always used, the confidence of something so enormous and so indifferent that it has never needed to apologize for the deception. The lie is this: the stars look close. Find two stars on a clear night that appear to sit beside each other, nearly touching like two grains of light, pressed into the same square inch of darkness. Your brain processes them as neighbors. Your visual cortex, shaped by millions of years of evolution calibrated for distances measured in feet and miles, tells you they are nearby objects separated by a modest gap. It is the same cognitive machinery that judges the distance to a tree, estimates the width of a river, or tracks the arc of a thrown stone. It is extraordinarily good at its job, and its job was never designed for this. Those two stars you are looking at may be separated by 40 light years. They may not even exist in the same spiral arm of the galaxy. One might be a dim red dwarf burning quietly, 6 light years from Earth, a cool ember of a star so faint it cannot be seen without a telescope. The other might be a blue supergiant blazing from 800 light years away, a furnace so violent that if it replaced our own sun, Earth would be incinerated within seconds. The night sky collapses all of this into a flat canvas, a dome of scattered light that your retina processes as though every star exists at the same approximate distance, as though the universe is a ceiling rather than an abyss. This is the most dangerous lie the cosmos tells, and it matters more than almost any other misconception in science. Because every casual assumption about alien civilizations visiting Earth, every late-night conversation about UFOs and government cover-ups and ancient astronauts, every science fiction film where a ship drops out of hyperspace above our planet in a matter of hours or days, every single one of these ideas rests on a foundation built from this lie. They assume, at their very core, that the stars are reachable, that the distances between them are large but manageable, that the universe is something like a very big ocean, and that a sufficiently advanced ship could cross it the way we once crossed the Atlantic. The universe is not a very big ocean. If you enjoy journeys that completely dismantle the way you see the cosmos, that replace comfortable assumptions with something harder and stranger and more awe-inspiring than anything science fiction has ever imagined, hit that like button and subscribe now. It genuinely helps this channel reach more people who want to understand the real scale of what we are living inside. Get yourself comfortable. Clear your mind of everything you think you know about the distances between stars. Because what we are about to examine is not a matter of opinion or interpretation, it is a matter of physics, and physics does not negotiate. Let's begin. Start with the simplest possible version of the problem. The nearest star to our Sun is Proxima Centauri, a small red dwarf that anchors the Alpha Centauri system approximately 4.24 light-years from Earth. 4.24. You can say that number in under 2 seconds. It sounds almost modest. It sounds like something a spacecraft could handle. 1 light-year is the distance light travels in a single year. Light moves at approximately 670 million miles per hour. In 1 second, light covers roughly 186,000 miles of distance, equal to circling Earth's equator more than 7 times. In 8 minutes, light travels from the surface of the Sun to your eyes. In 1 year, light covers approximately 5.88 trillion miles. Multiply that by 4.24. Proxima Centauri sits roughly 25 trillion miles from Earth. 25 trillion miles. Take a moment with that number, not as an abstraction to be quickly processed and set aside, but as a physical reality to be examined. If you began counting to 25 trillion at a rate of 1 number per second, never pausing, never sleeping, never stopping for any reason, you would require approximately 790,000 years to finish. Counting, you would begin before anatomically modern humans had fully spread beyond Africa. You would still be counting when the pyramids were built. still counting when Rome rose and fell, still counting through every century of recorded history, every war, every empire, every scientific revolution, every human life ever lived. And you would still have hundreds of thousands of years of counting remaining before you reach the distance to the nearest star. This is the distance to the closest possible destination, not the average interstellar distance, not a remote star in some far corner of the galaxy. The nearest neighbor, the cosmic equivalent of the house next door, and it sits 25 trillion miles away. Now consider the object humans have sent furthest into space. Voyager 1, launched in September of 1977, is the most distant human-made object in existence. It has been flying continuously for nearly 5 decades, without pause, without deceleration, without any engine firing to slow it down or redirect it. It travels at approximately 38,000 miles per hour, a velocity that is genuinely impressive by any terrestrial standard. A commercial airliner moves at roughly 560 miles per hour. Voyager travels about 68 times faster than that. A high-powered rifle bullet moves at approximately 1,700 miles per hour. Voyager is more than 20 times faster than a bullet. It has been flying at this speed since before most people reading this were born. In all that time, across all those decades of uninterrupted flight through the outer solar system and into interstellar space, Voyager 1 has covered approximately 15 billion miles. 15 billion miles sounds enormous, until you place it against the scale of interstellar distance. 15 billion miles is less than the distance light travels in a single day. Not 1 light year, not 1 light month, 1 light day. 24 hours of light travel. And a light day is 1/365th of a light year. And the nearest star is 4.24 light years away. At its current speed, Voyager 1 would require approximately 73,000 years to reach Proxima Centauri. 73,000 years. The entire span of human civilization, from the first agricultural settlements in the Fertile Crescent to the device you are using to watch this video, covers roughly 12,000 years. Voyager would need more than 6 times the entire length of recorded human history to reach the closest star. And when it arrived, it would not stop. It carries no braking mechanism, no retrorocket, no parachute, no system for deceleration. It would sail past the Alpha Centauri system at full speed and continue into the void beyond a frozen artifact, tumbling through darkness, the golden record on its side, carrying music and greetings and the coordinates of a world that launched it into an abyss it will never meaningfully cross. This is the reality that the night sky conceals so effectively. Now move outward from Proxima Centauri. Sirius, the brightest star in the night sky, sits 8.6 light-years from Earth. That is approximately 50 trillion miles. Vega, the brilliant blue-white star that marks the corner of the summer triangle, lies 25 light-years away, 147 trillion miles. Betelgeuse, the red supergiant that marks the shoulder of Orion and that billions of people have stared at on winter nights, sits approximately 700 light-years distant. Converting that number into miles produces a figure so large that writing it out would require a string of digits stretching across your screen. These are not exotic objects at the edge of the observable universe. These are ordinary stars in our immediate galactic neighborhood, the rough equivalent of nearby towns on the map of the Milky Way. And the distances between them are already so vast that Voyager's entire lifetime of travel represents a trivial fraction of the gap. The Milky Way galaxy itself spans approximately 100,000 light-years from edge to edge. Our solar system sits roughly 26,000 light-years from the galactic center, embedded in a minor spur of the Orion Arm, about 2/3 of the way out from the core. Light leaving one edge of the galaxy would need 100,000 years to reach the other side. Not a spacecraft, not Voyager, at its impressive 38,000 miles per hour. Light itself, traveling at 670 million miles per hour, needs 100,000 years to cross our single galaxy. A human lifespan is roughly 80 years. Light crosses the Milky Way in a time span equivalent to 1,250 consecutive human lifetimes, each one lived entirely in the dark between stars beginning and ending, in void. the destination no closer to the naked eye at the end than it was at the start. Here is an image that may help anchor this scale in something the mind can actually hold. Shrink the entire Milky Way galaxy down to the size of the continental United States. At this scale, the distance between individual stars becomes the distance between individual grains of fine sand. Our Sun and Proxima Centauri would be 2 grains sitting roughly 4 inches apart. That seems manageable. You could reach between them with your hand, but the next nearest Sun-like star, with a potentially habitable planet, might be a foot away. A civilization 1,000 light-years distant from Earth would be located somewhere in a different state entirely, perhaps as far as Chicago from New York. A civilization 5,000 light-years away would be on the opposite coast, and the full width of the galaxy 100,000 light-years stretches from the Atlantic to the Pacific. The galaxy looks crowded on a poster. It looks dense with stars when you photograph it as a smear of light across a dark sky. In reality, it is defined overwhelmingly by the emptiness between those scattered points. Most of the map is blank. Most of the space contains nothing at all. Not nothing in the way that the inside of a room is nothing. Nothing in the way that the interior of a vacuum, a void so complete that the nearest significant object in any direction is trillions of miles away, is nothing. The interstellar medium, the material that actually fills the space between stars, has a density of roughly 1 atom per cubic centimeter. The air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. The void between stars is roughly 25 quintillion times less dense than the air in your lungs. It is a vacuum more perfect than anything humans can produce in the most sophisticated laboratory on Earth. It is cold, hovering just a few degrees above absolute zero, the theoretical floor of temperature, below which nothing can go. It is dark, illuminated only by the faint and distant glow of stars that appear as points of light rather than sources of warmth. It is featureless. There are no landmarks, no waypoints, no reference frames, no road signs, nothing to orient a traveler except mathematics, and the faint shimmer of stars so far away they provide no useful navigational anchor. A spacecraft traveling between stars would spend decades or centuries or millennia surrounded by this, surrounded by absolutely nothing in every direction for distances so vast that the nearest significant object would be measured in trillions of miles. The experience has no human analogy. No ocean crossing, no polar expedition, no submarine dive, nothing in the catalogue of human physical experience approximates what it actually means to travel between stars. We speak of it as a journey because that is the only word we have, but it is something else. It is an exile so complete that the concept of home becomes a mathematical abstraction rather than a felt reality. This matters because the scale of that emptiness shapes everything else. Every other barrier to interstellar travel, the energy required, the time involved, the physical hazards of the void, is downstream from the simple, devastating fact of distance. The emptiness between stars is not large, the way mountains are large or oceans are wide. It is large in a way that belongs to a different category of existence entirely, a category that human intuition was not built to perceive, and that the night sky actively works to conceal. When someone imagines an alien civilization crossing the void to visit Earth, they are imagining a journey, a difficult one certainly, an impressive one perhaps, but a journey with a beginning, a middle, and an arrival. They are picturing the night sky as it appears to the naked eye, a field of reachable destinations, and assuming that sufficient intelligence and sufficient technology could navigate between those points, the way we navigate between cities. But the stars are not cities on a map. They are islands separated by oceans so wide that calling them oceans is itself an understatement, so severe it borders on absurdity. And the universe built those oceans not out of water or air, but out of the geometry of space itself. Out of the simple, unalterable, completely indifferent fact that matter and light and everything that exists must travel through the actual distance between 2 points mile by mile, year by year, without shortcut or exception. Even if they exist, the universe itself prevents them from getting here. This is the central truth, not a dramatic flourish, not a rhetorical device, a statement of physics that applies with equal force to every civilization that has ever existed in this cosmos or ever will. The wall of distance does not care how intelligent you are. It does not soften for civilizations that have spent 1,000,000 years developing technology we cannot imagine. It does not lower itself in deference to ambition or desperation, or the deep biological hunger to explore. It simply exists, immovable, indifferent, measured in trillions of miles and hundreds of thousands of light years, and it must be crossed in full 1 mile at a time. Now suppose a civilization accepts this. Suppose they have looked at the distances, stared the numbers in the face, and decided that they will cross the void regardless of what it costs. Suppose they have the will. Suppose they have the motivation. Suppose they have something on their world, perhaps resources, perhaps knowledge, perhaps simply curiosity of the kind that drove humans to step off continents into unknown seas that compels them to attempt the crossing. What happens when they start doing the mathematics? What happens when they calculate what physics demands in exchange for speed? Because distance, as devastating as it is a passive obstacle. It sits there, it waits, it does not actively resist the traveler. What turns the distance from an enormous challenge into something approaching a fundamental impossibility is the energy required to cross it in any time frame that a civilization could meaningfully plan for. And the energy required for interstellar travel is not merely large. It is governed by equations that grow in a way no engineering has ever learned to outrun. That is where we go next. Suppose you have accepted the distance. Suppose you have sat with the number 25 trillion miles, turned it over in your mind, to felt its weight, and decided that it will not stop you. Suppose your civilization has the will, the resources, and the institutional memory to plan across timescales that dwarf the entire history of human culture. You are going to cross the void. You are going to reach another star. The only question remaining is how, and the answer to that question leads immediately to a second wall, a wall built not from geometry but from thermodynamics, not from the passive fact of distance, but from the active, unforgiving mathematics of what it costs to move mass through space at the speeds required to make interstellar travel anything other than a geological timescale undertaking. The wall is energy, and the energy required to cross interstellar distances is not merely large in the way that building a skyscraper requires more materials than building a house. It is large in a way that is governed by equations whose outputs scale so aggressively that the numbers eventually stop feeling like numbers and start feeling like the universe saying no. Begin with a simple question. How fast does a spacecraft need to go to reach another star in any time frame that a civilization could meaningfully plan around? Not in the lifetime of a universe, not across geological epochs. In something approaching a human or civilizational timescale. Something that a society could launch, fund, and eventually receive news from. The answer most serious physicists and aerospace engineers settle on as a benchmark is 10% of the speed of light, commonly written as 0.1 c. At this velocity, a spacecraft would travel at approximately 67 million miles per hour. That is roughly 18,000 miles per second. For a sense of scale, consider that the Parker Solar Probe, the fastest human-made object ever built, reaches approximately 430,000 miles per hour at its closest approach to the Sun. 10% of light speed is more than 150 times faster than the fastest thing humanity has ever constructed. It is not an incremental improvement over current technology. It is an entirely different regime of physics. At 10% of light speed, the journey to Proxima Centauri takes approximately 42 years, one way. Not a round trip, not including the time needed to decelerate upon arrival. Just the transit from our solar system to the nearest star. A crew that departs at age 30 arrives at age 72, assuming nothing goes wrong, assuming the ship functions flawlessly for over 4 decades, assuming the human body endures the conditions of deep space without catastrophic failure. The return journey doubles that to 84 years. A mission to the nearest star and back consumes an entire human lifetime. But 42 years at least sounds survivable. It sounds like something a civilization could plan. And so the natural next question is simply, what does it cost to get there? The answer is where hope begins to collapse. To accelerate any object to a given velocity, you must supply kinetic energy equal to 1/2 of the object's mass multiplied by the square of its velocity. This is basic Newtonian mechanics, and it is already brutal at relativistic speeds. Consider a modest spacecraft, not a crude vessel, with life support and radiation shielding and food stores and communication arrays. Just a robotic probe, a small one, something roughly the mass of a compact car, approximately 1,000 kilograms. To accelerate 1,000 kilograms to 10% of light speed requires approximately 4.5 times 10 to the 17th joules of kinetic energy. Written out, that is 450 quadrillion joules. This number means nothing without context. So anchor it. A large nuclear power plant produces roughly 1 gigawatt of continuous power. 1 gigawatt equals 1 billion joules per second. Running that plant at full capacity for an entire year produces approximately 31.5 petajoules. Accelerating our tiny 1,000 kilogram probe to 10% of light speed would consume the entire output of a large nuclear power plant running continuously for roughly 14 years. 14 years of a facility that cost billions of dollars to build, that powers 1 million homes funneled entirely and without interruption into pushing a car-sized robot to a velocity that still requires 4 decades to reach the nearest star. Now, consider the total energy humanity produces across all sources in a single year. Every power plant, every engine, every fire, every solar panel, every wind turbine, every dam on every river on Earth. The total comes to approximately 5.8 times 10 to the 20th joules. The energy needed to accelerate our 1,000 kilogram probe to 10% of light speed is roughly 1/300th of global annual energy production for a single probe, with no deceleration, no return trip, no crew, no mission beyond arriving and continuing to sail past. The most famous nuclear weapon ever detonated, the device dropped on Hiroshima in August of 1945, released approximately 63 terajoules of energy. The kinetic energy of our modest probe at 10% of light speed is equivalent to roughly 7,000 Hiroshima detonations, 7,000 nuclear explosions compressed into the motion of a single small spacecraft. That is the energy price for the cheapest possible interstellar ticket in physics, and we have not yet paid for stopping. A probe arriving at Proxima Centauri at 10% of light speed will sail through the star system in a matter of hours unless it decelerates. It carries no momentum-absorbing mechanism, no aero-braking option in the vacuum of interstellar space, no gravity, well large enough to capture it naturally at that velocity. To stop it must apply thrust in reverse, dissipating the same kinetic energy it took 14 years of a nuclear power plant to build. The energy budget doubles, 2 sets of 14 years of full power generation, for a probe the size of a car to visit the nearest star and halt when it arrives. Now scale this to something approaching a meaningful mission, a crewed vessel. The absolute minimum for a sustained human presence in deep space would include life support systems, water recycling, food production or storage, radiation shielding, navigation equipment, communication arrays, medical facilities, structural, materials, and the crew themselves. Even the most stripped-down, crude vessel imaginable masses at minimum in the hundreds of thousands of kilograms. Realistic estimates for a functional interstellar ship range from 1 million to 100 million kilograms. The energy requirements scale directly with mass. A 1 million kilogram spacecraft, barely large enough by most analyses to sustain even a skeleton crew across interstellar distances, requires 1,000 times more energy than our 1 to 1,000 kilogram probe. That is 14,000 years of a nuclear power plant's output for the acceleration phase alone. A 100 million kilogram vessel requires 100 million times more energy than the probe. The numbers ascend into territory where they cease to function as practical quantities and begin to read as pure mathematics sequences of digits that describe a physical reality so remote from current capability that the gap between here and there is not a gap but a chasm of unknown and possibly unlimited depth. This is where the tyranny of the rocket equation enters. In 1903, a Russian schoolteacher and self-taught mathematician named Konstantin Tsiolkovsky derived an equation describing the relationship between a rocket's velocity, the velocity of its exhaust, and the ratio of its initial mass to its final mass. The equation is compact, it is elegant, and for anyone dreaming of interstellar travel, it is devastating. The core problem that the Tsiolkovsky equation reveals is circular and inescapable. To go faster, you need more fuel, but more fuel means more mass at the start of the journey. More mass means you need still more fuel to accelerate that additional mass. More fuel adds more mass, which demands yet more fuel. The feedback loop has no exit. Fuel requirements do not scale proportionally with the desired velocity. They scale exponentially. And at relativistic velocities, the exponential curve becomes so steep that it produces answers the universe seems to have designed specifically to discourage. For chemical rockets, which produce exhaust velocities of roughly 4.5 kilometers per second, reaching even 1% of light speed would require a fuel-to-payload ratio so extreme that the spacecraft would need to be composed almost entirely of propellant, with the actual mission payload representing a nearly negligible fraction of the total mass. Reaching 10% of light speed with chemical propulsion does not merely strain credibility, it is mathematically excluded. The quantity of fuel required is not just impractical, it exceeds the mass of observable matter in a meaningful region of space. The exponential function grows that mercilessly. Nuclear propulsion offers genuine improvements. A nuclear thermal rocket, which heats propellant using a fission reactor rather than combustion, produces exhaust velocities roughly twice those of chemical rockets. Project Orion, a serious engineering concept developed by physicists including Freeman Dyson in the late 1950s, proposed detonating nuclear bombs in rapid sequence behind a spacecraft to generate thrust. Orion's designers estimated it could achieve perhaps 3 to 5% of light speed. This remains one of the highest velocities ever calculated for a physically realizable propulsion system using known technology. And it required a spacecraft roughly the size of a city block and a stockpile of nuclear warheads that would make any nation's arsenal look modest. It was abandoned not because the physics failed, but because detonating thousands of nuclear weapons in Earth's atmosphere proved diplomatically and environmentally untenable. 5% of light speed, that is the outer limit of the most aggressive nuclear propulsion concept ever seriously studied. At 5% of light speed, the journey to Proxima Centauri takes 84 years, 2 human lifetimes one way, and getting there requires a ship larger than most buildings and a fuel load that could sterilize a continent. Fusion propulsion represents the next theoretical step. Fusion releases roughly 4 times more energy per kilogram of fuel than fission and hydrogen. The raw material of fusion is the most abundant element in the universe. A working fusion drive could theoretically achieve exhaust velocities of several percent of light speed, bringing interstellar transit times down toward decades rather than centuries for nearby stars. It is the most promising propulsion concept within the boundaries of known physics. It is also a technology that humanity has been attempting to develop for more than 70 years without achieving net energy gain from a sustained reaction. The challenge of controlled fusion is not a lack of understanding of the underlying physics. Scientists have understood thermonuclear fusion since the 1950s. The challenge is containment. Fusion requires heating hydrogen isotopes to temperatures exceeding 100 million degrees Celsius, roughly 6 times hotter than the core of the Sun. At these temperatures, matter exists as plasma, a state so energetic that it annihilates any physical container it contacts. The solution is magnetic confinement, using powerful magnetic fields to suspend the plasma in a vacuum, preventing it from touching the reactor walls. But plasma is not cooperative. It writhes, oscillates, and develops instabilities that punch through magnetic containment in milliseconds, extinguishing the reaction before it can produce meaningful energy output. The history of fusion research is a catalogue of deferred promises. The International Thermonuclear Experimental Reactor, the most ambitious fusion experiment ever constructed, has been under development for decades at a cost exceeding $25 billion. Its goal is to demonstrate net energy gain from a fusion reaction sustained for minutes. The energy required to push even a modest spacecraft to 10% of light speed demands power outputs millions of times greater than what ITER aims to achieve, sustained not for minutes, but for months or years of continuous acceleration. The gap between current fusion research and fusion-powered starships is not a gap that the next generation of engineers will close. It is a succession of fundamental breakthroughs, each one uncertain, each one building on the last, stretching across a timeline that no honest physicist will attach a specific date to. The most energy-dense fuel permitted by the laws of physics is antimatter. When a particle of matter meets its antimatter counterpart, they annihilate each other, completely converting 100% of their combined mass into energy. According to Einstein's equation, relating mass and energy through square of the speed of light. No other reaction in physics approaches this efficiency. Chemical combustion converts less than 1/10,000,000% of fuel mass into energy. Nuclear fission converts roughly 0.1%. Nuclear fusion converts roughly 0.7%. Antimatter annihilation converts 100%. It is the theoretical ceiling, the absolute maximum energy that physics permits per kilogram of material. Even antimatter is not enough to make interstellar travel straightforward. To accelerate a 1,000 kilogram probe to 10% of light speed using antimatter propulsion at perfect efficiency would require approximately 500 kilograms of antimatter combined with 500 kilograms of ordinary matter. 500 kilograms sounds almost reasonable, until you learn what humanity has actually produced. The total quantity of antimatter created by every particle accelerator on Earth across the entire history of physics amounts to approximately 20 nanograms. A nanogram is 1/1000th of a gram. 20 nanograms would be invisible to the naked eye. It would not register on any kitchen scale or most laboratory instruments. If you gathered together every atom of antimatter ever produced by every accelerator in every country across every decade of particle physics research, the resulting speck would sit on the tip of a needle and vanish from sight before you could photograph it. Producing a single gram of antimatter using current technology would require energy inputs of approximately 25 million billion watt-hours and a cost estimated at around $25 trillion. $25 trillion exceeds the gross domestic product of the United States. And that is for 1 gram. The fuel requirement for our probe is 500,000 grams, 500 kilograms. The cost and energy inputs scale accordingly into numbers that belong not to economics, but to mythology. Producing 500 kilograms of antimatter using any technology remotely related to current approaches would require the entire energy output of human civilization sustained for millions of years, not decades, not centuries, millions of years, directed entirely toward this one task with no energy left over to run cities or hospitals or the farms that feed the people operating the accelerators. This is the energy wall in its most concrete form, not a poetic metaphor, not an exaggeration for effect, a direct calculation from known physics applied to the most energy-efficient fuel the universe permits. Here is where the argument typically pivots. Here is where someone says, but what about a civilization far more advanced than ours? What about a Type 2 civilization on the Kardashev scale, one that has harnessed the full energy output of its host star? A sun-like star produces approximately 3.8 times 10 to the 26th watts of continuous power. That is an almost incomprehensible quantity of energy. Would not such a civilization find the energy cost of interstellar travel trivial? The answer requires careful thinking because it contains a subtle but critical error. A Type 2 civilization can generate the energy more easily than we can. They can afford the fuel bill more comfortably, but they cannot pay a smaller bill. The bill is set by physics, not by economics. The minimum kinetic energy required to accelerate a given mass to a given velocity is fixed by the relationship between mass velocity and the speed of light. No amount of available power changes this minimum. The floor is set by the universe, not by the sophistication of the engine. Consider an analogy from everyday physics. Lifting a 1 kilogram object 1 meter against Earth's gravity requires approximately 10 joules of energy. This is true whether you lift it with your bare hand, a block and tackle, or a precision robotic arm engineered by the most advanced civilization imaginable. the mechanism changes. The energy requirement does not. You can approach the theoretical minimum with greater efficiency, losing less energy to heat and friction. But you cannot go below the minimum because the minimum is determined by the gravitational field and the mass of the object, not by the quality of your engineering. The same principle governs interstellar propulsion. The minimum energy to accelerate 1 kilogram to 10% of light speed is fixed. A Type 2 civilization can generate this energy far more easily than a Type 1, but they must still generate it. They must still expend it. And as the mass of the ship scales upward, so does the bill without mercy, without exception. A civilization commanding the full power of a star could theoretically accelerate a large interstellar vessel to a significant fraction of light speed in a matter of days or weeks rather than years. That is a genuine advantage. But each such mission still costs a measurable fraction of their stellar energy budget. Launching dozens or hundreds of such missions simultaneously would impose costs that even a Type 2 civilization would feel. Launching thousands, the kind of systematic exploration needed to visit even a small fraction of nearby star systems, would consume resources at a level that strains the concept of sustainability, even for a star-harnessing civilization. And none of this addresses the deeper constraints. More energy does not make the ship go faster than light. More energy does not shorten the distance between stars. More energy does not eliminate the radiation hazards of the interstellar medium or prevent the social and mechanical degradation of a vessel in transit for centuries. More energy does not stop the clock. The energy wall does not crumble before advanced technology. It recedes slightly, allowing more capable missions at greater cost. But the wall's fundamental character does not change because its fundamental character is determined by physics, by the speed of light as an absolute limit, by the relationship between mass and kinetic energy, by the conservation laws that govern every process in the universe without exception. These are not human limitations projected onto alien civilizations. They are the rules of the game that every civilization in this cosmos must play by, regardless of age, intelligence, or accumulated technological sophistication. The universe does not issue exemptions. It does not offer discounts for ambition. It states its price, and it does not negotiate. Even if they exist, the universe itself prevents them from getting here. The energy required to move mass between stars is enormous, fixed, and universal. It represents only the first payment the universe demands for an interstellar journey. The second payment is extracted not from a civilization's energy reserves, but from something far less replaceable. It is extracted from time. Time does not care about your mission. This is the first thing to understand about the third wall. Distance is passive. It sits between 2 points and waits. Energy is transactional. You pay it, and you receive velocity in return. But time is neither passive nor transactional. It moves in one direction at one speed, without regard for what you have built, what you have sacrificed, or how long your civilization has spent preparing for the journey. It erodes everything it touches. It dissolves institutions, languages, purposes, and people with the same indifferent efficiency. It brings to the erosion of mountains. And for any civilization attempting to cross the interstellar void, time is not merely a constraint. It is an adversary that cannot be fought, bargained with, or outlasted. Begin with the simplest version of the problem. At 10% of light speed, the journey to Proxima Centauri takes 42 years one way. This is the optimistic case, the nearest star, the shortest possible interstellar trip. 42 years of continuous flight through a vacuum so empty and hostile that no human analogy adequately describes it. A crew that departs at age 30 arrives at age 72, assuming perfect health, perfect ship function, and no unforeseen complications across 4 decades of complete isolation from every support system civilization provides. 42 years is a human lifetime, compressed into a single mission. The person who steps onto the ship is recognizably the same biological entity as the person who steps off, but they are not the same in any meaningful psychological or social sense. Everyone they knew on Earth has aged with them or died. Parents likely gone, childhood friends elderly or absent. The cultural references that shaped their identity, the music, the politics, the shared events that define a generation, have been replaced by 40 years of new history they were not present for. They return as strangers to a world that did not pause for them, carrying memories of a departure that most of the people who witnessed it can no longer clearly recall. And this is the best case. Alpha Centauri is the closest star. It is the absolute minimum interstellar distance. Most stars in the Milky Way are not 4 light-years away. They are tens, hundreds, or thousands of light-years distant. The average separation between stars in the galactic neighborhood surrounding our Sun is approximately 4 to 5 light-years, but this average conceals our enormous variation. Many of the stars most likely to host habitable worlds are scattered across distances that transform the 42-year journey to Proxima Centauri into a brief warm-up exercise. At 10% of light speed, a journey to a star 100 light-years away takes 1,000 years, 1 millennium. A civilization that launched such a mission would need to sustain interest, funding, political will, and institutional memory across a time span during which on Earth the Roman Empire rose and fell, the Renaissance occurred, the scientific revolution unfolded, the Industrial Age began, and humanity reached the moon. Every one of those transformations happened within 1,000 years. Every one of them would be invisible to a crew in transit, unknown to them, unreachable, separated by the same communication delays that make interstellar coordination a mathematical impossibility. A star 500 light-years away requires 5,000 years at 10% of light speed. A star 1,000 light-years distant requires 10,000 years. These numbers do not merely challenge human endurance. They mock it. No individual survives them. No crew survives them. No institution on Earth has survived them. The oldest continuously operating university on Earth is roughly 900 years old. The oldest known continuous governmental institution is perhaps 1,000 years in age. 10,000 years reaches back before the invention of writing, before the construction of the first cities, before the domestication of the horse. It is not a travel time, it is an epoch. And 10% of light speed is the ambitious case. The velocity that already demands energy expenditures equivalent to thousands of nuclear detonations for a car-sized probe. For a vessel large enough to sustain human life, 10% of light speed may represent an aspiration so far beyond current capability that it functions as fiction rather than engineering. A more physically realistic velocity for a large interstellar vessel, accounting for fuel mass constraints and structural limitations, might be 1% of light speed. At 1% of light speed, roughly 6.7 million miles per hour, the journey to Proxima Centauri takes 420 years. A star 100 light-years away requires 10,000 years. A star 1,000 light-years distant requires 100,000 years. 100,000 years ago, Homo sapiens was sharing the planet with Neanderthals. No human language, no human building, no human institution, no human technology has survived 100,000 years. Nothing we have ever made has endured even a fraction of that span. The oldest known stone structures are perhaps 12,000 years old. The oldest known continuous cultural tradition traced through archaeology and genetics is perhaps 40,000 years old, and even that thread is so attenuated across time that calling it continuous is a generous interpretation. 100,000 years is not a civilizational timescale, it is a geological one. Species change across such periods. Continental configurations shift. Ice ages begin and end. The very concept of a mission lasting this long does not belong in the category of engineering challenges. It belongs in the category of fantasies, so disconnected from observable reality that examining them requires a deliberate suspension of every lesson history has ever taught. This is where the concept of the generation ship enters the conversation. The idea has an elegant simplicity. If no individual can survive the journey, then perhaps a population can. Build a vessel large enough to sustain a self-reproducing community. The original crew lives, works, ages, and dies aboard the ship. Their children are born in transit. Their children's children are born in transit. Generation after generation passes through life inside the vessel, each one inheriting the mission from the last, carrying it forward across centuries or millennia until the final generation arrives at the destination. The journey becomes not the story of individuals, but the story of a people, a civilization in miniature, sustained across the void, arriving at a new world as the culmination of a multi-generational act of collective will. In abstraction, this is almost beautiful. In practice, it is a catalogue of catastrophic failure modes, so comprehensive and so deeply rooted in observable human behavior that the concept collapses under examination before it even reaches the engineering challenges. Begin with the biology, because the biology must work before anything else matters. A generation ship must maintain a genetically viable population across hundreds or thousands of generations. Inbreeding is the first threat, and it is not a distant or theoretical one. When a small founding population is isolated from all outside genetic input and reproduces only within itself, the frequency of harmful recessive genes increases with each generation. Genetic diversity, the raw material of adaptability and biological resilience, erodes. The population becomes increasingly vulnerable to diseases it might otherwise resist, to environmental stresses it might otherwise adapt to random genetic events that might otherwise be diluted by the diversity of a larger gene pool. Population genetics research suggests that a minimum viable population for long-term genetic health, sufficient to avoid inbreeding depression and maintain meaningful diversity across many generations, requires at minimum several thousand individuals. Some analyses place the number at 5,000, others suggest 10,000 or more. This is not a skeleton crew of determined volunteers. This is a small city, a city that must be housed, fed, given meaningful work, provided with social structures governed, educated, kept healthy, and sustained indefinitely inside a sealed metal container, hurtling through a vacuum at millions of miles per hour. The mass of a vessel, capable of housing 10,000 people, providing each with living space, growing food, recycling water and atmosphere, managing waste, maintaining medical facilities, generating power, providing manufacturing capability for replacement parts, and shielding the population from the radiation environment of interstellar space would be enormous. Estimates for such a vessel range into the tens of millions of kilograms at minimum, possibly far more. The energy requirements for accelerating this mass to any significant fraction of light speed would compound the already staggering figures described in the previous section by orders of magnitude. But population size is only the entrance to the biological problem. A closed ecosystem must recycle all resources with perfect efficiency indefinitely, with no external input and no possibility of resupply. Every molecule of water must be recovered, purified, and redistributed. Every gram of carbon must cycle through the biological systems of the ship without permanent loss. Every breath exhaled must eventually become a breath available to inhale again. The atmosphere must be maintained within narrow chemical tolerances. The food production system must yield sufficient calories and nutritional balance for the entire population across every season of a journey, lasting thousands of years. No closed ecological system has ever been sustained by humans for more than a few years. Biosphere. 2. The most ambitious attempt at a sealed human ecosystem ever. Constructed enclosed 8 people in a 3-acre facility in the Arizona desert in 1991. It had the advantage of Earth's gravity. It had access to natural sunlight. It sat within a functioning magnetosphere that shielded it from cosmic radiation. It was built with the full resources of a wealthy modern economy behind it. And within 16 months, oxygen levels had dropped to dangerous lows. Carbon dioxide had risen erratically. Most of the vertebrate species introduced into the system had gone extinct, and the experiment required external intervention to prevent the crew from suffocating. 8 people, 3 acres, Arizona sunshine, 2 years. A generation ship would need to sustain thousands of people in a sealed metal environment in a vacuum, without natural light or gravity, without magnetic shielding from cosmic radiation, without any possibility of external intervention, without resupply of any kind for thousands of years, without a single critical system failure propagating into irreversible catastrophe. The distance between what Biosphere 2 achieved and what a generation ship requires is not a distance that better engineering gradually closes. It is a difference in category, not in degree. The engineering challenges of life support across millennia are matched in severity by the social challenges of maintaining a coherent mission across the same span. Human societies are not stable across centuries, let alone millennia. They fragment, reorganize, and collapse with a regularity so consistent across cultures and continents that it functions as something approaching a law. No government on Earth has survived 1,000 years in continuous form. No language has remained unchanged across a millennium. No set of values, no cultural framework, no institutional structure has propagated itself without fundamental transformation across 10 or 20 generations of human beings who each renegotiated their relationship with the traditions they inherited. Imagine the reality aboard a generation ship 500 years into a 10,000-year voyage. The original crew is 20 generations dead. Their names exist in databases that fewer people consult with each passing century. No living person aboard has ever felt wind stood beside an ocean or looked up at a sky that was not a ceiling. The mission, conceived and launched by people so distant in time they have acquired the quality of mythology, is now the inheritance of a population that had no say in accepting it. Their language has drifted. The words used by the founders to describe the mission's purpose have shifted in meaning across centuries of isolation. Languages in isolation change faster than languages in contact with other speakers. Within a few centuries, the original mission documents may require translation. Within a millennium, they may be as opaque as ancient texts, requiring specialists to interpret, subject to the same creative reinterpretation that all ancient texts eventually receive. Their cultural framework has been rebuilt multiple times. Every crisis, every resource shortage, every epidemic, every power struggle produces new social arrangements. Some of these arrangements bear a recognizable relationship to the civilization that launched the ship. Others do not. The ship has been through revolutions. It has been through periods of authoritarian consolidation, followed by fragmentation, followed by new consolidation. It has developed religious traditions that did not exist at departure, philosophical frameworks that emerged from the specific conditions of shipboard life, art forms that have no referent in any culture that ever existed on a planetary surface. Some of the people aboard believe the mission is sacred, a covenant with ancestors whose wisdom must be honored regardless of personal cost. Others believe the mission is a tyranny, a sentence imposed on the living by the long dead, who had no right to conscript their descendants into a project those descendants never chose. A third faction has developed a cosmology in which the ship itself is the natural and eternal state of existence, the stories of a home world and a destination being understood as metaphors for spiritual states rather than physical realities. These factions do not simply disagree. They compete for resources, for governance authority, for the educational curriculum that shapes each new generation's understanding of why they exist and where they are going. These conflicts will not always be resolved through deliberation. Violence is not merely possible aboard a generation ship across a timeline of thousands of years. Given the length of confinement, the scarcity of resources in a closed system, and the absence of any external moderating influence, it is statistically certain. The only question is its frequency and its consequences. What happens when a faction seizes control of the ship's navigation systems and alters the course? What happens when a population that has lived inside a metal vessel for 50 generations decides through genuine democratic consensus that, continuing toward a destination none of them have ever seen, is less important than reorganizing their society around principles incompatible with the mission's original mandate? What happens when the knowledge required to maintain a critical system is held by a specialist who dies in an epidemic before training a successor, and the institutional memory of how that system works is simply gone? These are not hypothetical disasters invented for dramatic effect. They are extrapolations from the documented behavior of human communities under conditions far less extreme than those of an interstellar generation ship. Isolated communities on Earth, communities with access to sunlight and fresh air, and the theoretical possibility of leaving still experience ideological fragmentation, social collapse, and the gradual erosion of specialized knowledge within a few generations. A vessel in which there is no possibility of leaving, no outside world to provide new ideas or new people or new resources. No escape valve for the pressure that confinement creates would face these forces in their most concentrated and unrelenting form. Mechanical degradation runs in parallel with social degradation, and the two interact in ways that amplify both. No machine lasts forever. Every material degrades. Metals fatigue under cyclic stress. Seals lose their elasticity. Bearings wear. Electronics accumulate radiation damage that slowly corrupts their function. Lubricants break down into compounds that gum rather than smooth the mechanisms they were meant to protect. In ordinary engineering environments, degradation is managed through inspection, maintenance, and replacement. Components are monitored, react, or swapped out. Systems are overhauled on regular schedules by trained personnel with access to replacement components and reference materials. A generation ship must manage this degradation across thousands of years in an environment where replacement components must be manufactured from onboard materials that are finite, where the trained personnel of one generation may not fully transfer their knowledge to the next, and where every repair consumes resources that cannot be replenished from outside. The mathematics of reliability engineering make the challenge precise and unambiguous. A system with a 99.9% annual survival probability, meaning a 1 in 1,000 chance of catastrophic failure in any given year, has less than 1% chance of surviving 10,000 years without a single failure. Functionally zero. To achieve even a 50% probability of surviving 10,000 years intact, a system must have an annual failure probability below 1 in 14,000. These are reliability levels that no human technology has ever approached or even closely targeted as a design goal. They must be maintained not for one system but for thousands of interdependent systems that must all function simultaneously, each one's failure potentially cascading through the others in ways that no pre-departure analysis could have fully anticipated. Now introduce relativistic time dilation into this picture, because here is where the physics offers what appears to be a solution and then takes it away with the other hand. Special relativity, confirmed by more than a century of increasingly precise experimentation, describes a phenomenon that sounds almost miraculous when first encountered. As an object accelerates toward the speed of light, time passes more slowly for that object relative to observers who remain stationary. At 90% of light speed, a clock aboard a spacecraft ticks at roughly 44% of the rate of a clock on Earth. A journey that takes 100 years in Earth's reference frame would feel like approximately 44 years to the crew. At 99% of light speed, the crew would experience only about 14 years for every 100 years that pass at home. At 99.9%, the compression becomes more dramatic still. In principle, a crew traveling at these velocities could survive journeys to stars hundreds of light years away without dying of old age. They would arrive biologically young, having experienced only a fraction of the time elapsed in the outside universe. This is not science fiction. It is a confirmed consequence of how spacetime actually functions. The effect has been measured in particle accelerators, in atomic clocks flown on aircraft, in the timing corrections required to keep GPS satellites accurate. Time dilation is real, but time dilation solves the problem for the travelers, while catastrophically compounding it for everyone else. While 14 years pass aboard a ship traveling at 99% of light speed, 100 years pass on Earth. The crew arrives at their destination biologically young and cognitively intact. They step off the ship to find that every person they knew on their home world is dead. Every institution that funded the mission has reorganized beyond recognition. The civilization they represented has had a full century to transform in ways they cannot predict or prepare for. They are not merely far from home in space, they are far from home in time. They have traveled into the future of their own civilization while experiencing only a fraction of the intervening years. Communication compounds this isolation into something approaching total severance. Messages sent home after arrival travel at light speed, meaning they take the same number of years to reach Earth as the light years of distance traversed. A reply, if one comes, arrives decades or centuries later. The conversation, if it can even be called, that consists of messages in bottles separated by lifetimes. The crew and their home civilization are not separated. They are disconnected. There is no thread connecting them that moves faster than light, and light is not fast enough. And reaching 99% of light speed brings the energy wall crashing back magnified. The relativistic mass increase at this velocity means the energy required for acceleration is multiplied by a factor of roughly 7 compared to the already staggering costs of 10% of light speed. The fuel requirements for a crewed vessel become figures that belong to the energy output of stars, not civilizations. Time dilation does not come free. It is purchased at a cost that makes every other aspect of the energy problem look like a rounding error. This is the trap at the heart of the time barrier. At achievable speeds, journeys take so long that they outlast civilizations. At extreme speeds, time dilation makes journeys survivable for the crew, but demands energy that makes departure essentially impossible. There is no velocity at which interstellar travel is simultaneously affordable and timely. The universe has arranged its constants with a completeness that blocks every attempted shortcut. Every solution to one problem tightens the constraints of another. Reduce travel time and energy costs become impossible. Add shielding against radiation and mass grows beyond what propulsion can move. Extend mission duration, and the ship, the crew, and the civilization behind them all begin to dissolve. The pattern does not have a weakest link. It is not a chain waiting to be broken by a single critical insight. It is a web, and every strand of the web is woven from the same material. The physical constants of the universe, the speed of light, the conservation of energy, the second law of thermodynamics, the nature of biological organisms, the behavior of human societies across time. These constants did not arise from human limitations. They were the conditions of the universe before the first star ignited, before the first planet formed, before anything capable of contemplating them existed to do so. They apply to everyone. Even if they exist, the universe itself prevents them from getting here. Distance sets the stage, energy sets the price. Time collects the debt that distance and energy leave unpaid, and it collects without mercy from the ship and its systems, from the crew and their descendants, from the civilization that launched them and the purpose they were sent to. En serve. No mission that crosses interstellar distances escapes the compounding interest of time. It accumulates in every cell of every biological organism aboard, in every crystal lattice of every metal component, in every line of every institutional memory that must somehow survive across spans that have never preserved anything human beings have ever built. The void between stars is not merely empty, it is patient. It has all the time in the universe, and it will wait out any traveler, any ship, any civilization that attempts to cross it. It has been waiting for 13 billion years already. A few thousand more years means nothing to it. To the civilization in transit, to the people born and dying inside a metal shell between the stars, those same years are everything. But suppose a civilization looks at all of this and refuses to be stopped. Suppose they accept the energy cost, accept the time, accept the social and mechanical degradation, and press forward anyway. There is still one more dimension of the problem that has not yet been examined, because the void itself is not passive. It does not merely wait for travelers to exhaust themselves crossing it. At the velocities required for any interstellar mission with a civilizational timescale shorter than geological, the void becomes actively lethally hostile in ways that no armor can fully address and no shield can completely deflect. That is where we go next. The void looks safe. This is the third great lie the universe tells about interstellar travel, and it is in some ways the most insidious of the three. The night sky lies about distance, making the stars appear close. The equations of propulsion lie about accessibility, making speed seem like merely a matter of sufficient ambition. And the emptiness of interstellar space lies about danger presenting itself as a neutral medium, a featureless vacuum through which a spacecraft might glide unimpeded like a ball rolling across a frictionless floor. It is not a frictionless floor. At the velocities required to cross interstellar distances in any timescale shorter than geological, the emptiness of space transforms into something that functions from the perspective of a spacecraft as a continuous and relentless bombardment. The particles that populate interstellar space are sparse beyond any earthly analogy. but at relativistic speed sparse becomes irrelevant. What matters is not the density of the medium, but the rate at which a moving object encounters it. And at 10% of light speed, a spacecraft encounters the interstellar medium not as an occasional event, but as a perpetual storm of particles arriving, with energies that no material known to physics can indefinitely withstand. Begin with the most straightforward hazard: dust. The interstellar medium contains microscopic solid particles, grains of silicate, and carbon compounds, remnants of stellar outflows and supernova ejecta, distributed through the galaxy at extremely low densities. In the denser regions near the galactic plane, the concentration reaches perhaps 1 dust grain per cubic kilometer. In some regions, it is even sparser. By any ordinary standard, this is an almost perfect vacuum. A spacecraft traveling through it under normal circumstances would encounter these particles so rarely that they would represent a negligible concern. But a spacecraft is not traveling under normal circumstances. It is traveling at 10% of light speed. And at that velocity, the kinetic energy of a collision is determined not by the mass of the projectile alone, but by the square of the relative velocity between the projectile and the spacecraft. The formula is unforgiving. A dust grain massing 1 microgram, a speck so small it would be invisible to the naked eye. Striking a spacecraft at 10% of light speed delivers kinetic energy equivalent to approximately 100 kilograms of TNT. Not 1 kilogram, 100. A single invisible particle of interstellar dust, moving at a velocity that a spacecraft must achieve to reach another star in a reasonable time, hits with the force of a large conventional bomb. Let that settle for a moment. A particle of dust, invisible, weighing less than a bacterium, hitting with the force of 100 kilograms of explosive. Over a journey spanning light years, a spacecraft with a cross-sectional area of just a few hundred square meters would encounter thousands of such particles. Each impact would deliver explosive force to whatever material it struck. At 10% of light speed, even hydrogen atoms, the single protons that constitute the most abundant component of the interstellar medium, carry energies in the mega-electron-volt range. Each individual proton deposits a tiny amount of energy when it strikes the hull, but the flux is continuous. Every second of every minute, of every hour, of every year of the journey, the forward face of the spacecraft is being struck by a stream of particles that in aggregate functions as a sustained particle accelerator beam directed at whatever material stands between the crew and the void. The effects of this bombardment are cumulative and irreversible. At the atomic level, energetic particle impacts displace atoms from their positions in crystal lattices, the regular geometric arrangements that give metals their strength and structural integrity. Each displaced atom creates a defect in the material's microstructure. One defect is harmless. 1,000 defects in a small volume begin to alter the material's mechanical properties. 1,000,000 defects accumulated over years of continuous bombardment can transform a strong, ductile metal into a brittle, weakened substance, prone to cracking under stresses it would previously have handled without difficulty. This process, called radiation damage or displacement damage, is well understood from the engineering of nuclear reactors, where structural materials are exposed to intense neutron fluxes. Materials in nuclear reactors must be replaced on regular schedules, precisely because radiation damage accumulates and eventually compromises their structural function. A spacecraft in interstellar transit faces a radiation environment that makes the interior of a nuclear reactor look manageable. The particle fluxes are lower in terms of number density, but the energy per particle is higher, and the exposure duration is not years but decades or centuries. There is no replacement schedule. There is no maintenance facility waiting at the end of a shift. There is only the accumulation of damage year after year in materials that must perform their structural and protective functions without interruption, regardless of what the particle flux is doing to them at the atomic level. The forward heat shield, the structure that bears the brunt of this continuous bombardment, faces the most severe conditions. At 10% of light speed, even the sparse hydrogen of interstellar space becomes, from the perspective of the shield, a river of relativistic protons striking at roughly 30 million meters per second. These protons do not merely bounce off, they penetrate into the material, depositing their energy over a characteristic depth determined by the stopping power of the shield material. Some of this energy manifests as heat, some manifests as ionization of the surrounding atoms, some manifests as nuclear reactions when energetic protons strike the nuclei of heavier atoms in the shield material, producing secondary particles that travel deeper into the structure. The shield erodes, not quickly by any ordinary standard, but continuously, without pause, without reversal, without any mechanism that can replace the material being ablated away, unless the ship can manufacture new shielding from onboard resources. And manufacturing new shielding requires energy and raw materials, and the kind of industrial capability that adds mass to the vessel, which adds to the energy requirements for propulsion, which feeds back into every constraint already discussed. Now consider the biological implications of this radiation environment. The human body is extraordinarily sensitive to ionizing radiation. Radiation damages DNA, the molecular blueprint that every cell uses to reproduce itself accurately. Most DNA damage is repaired by the cell's own molecular machinery, which constantly monitors the genome and corrects errors. But when damage rates exceed the repair capacity of this machinery, errors accumulate. Some of these errors are corrected, imperfectly introducing mutations. Some mutations are neutral, some are harmful. Some initiate the cascade of molecular errors that eventually produces cancer. The radiation exposure aboard a spacecraft in interstellar transit at 10% of light speed would come from multiple sources simultaneously. The steady flux of interstellar hydrogen and helium nuclei striking the forward shield would produce secondary radiation that penetrates deeper into the vessel. Cosmic rays, high-energy particles, accelerated to near light speed by astrophysical processes, would pass through the hull and the shielding and the bodies of the crew as though none of these obstacles existed, and the spacecraft's own speed would transform the relatively gentle electromagnetic environment of interstellar space into a blue-shifted bath of harder, more penetrating radiation as the Doppler effect compresses the wavelengths of incoming photons toward the energetic end of the pulse spectrum. Astronauts aboard the International Space Station, protected to some degree by Earth's magnetic field and operating at velocities a tiny fraction of interstellar speeds, receive radiation doses roughly equivalent to the maximum annual exposure permitted for nuclear industry workers. Over a career of perhaps 200 days in space, an astronaut accumulates a radiation dose that measurably increases their lifetime cancer risk. Beyond Earth's magnetosphere, in the deep space environment that any interstellar mission would traverse, the radiation environment is significantly more intense. A crew traveling at 10% of light speed through the interstellar medium would receive radiation doses that dwarf anything experienced by astronauts in low Earth orbit. Over a 42-year journey to Proxima Centauri, the cumulative biological damage would be severe. The cancer risk for crew members surviving the trip would be extraordinarily high. Cognitive function, which is particularly sensitive to certain types of radiation damage, because neurons do not generally regenerate after being killed, would degrade over time. The reproductive viability of crew members would be compromised. Children born aboard the ship would be born into a radiation environment that imposes genetic damage at rates higher than background terrestrial levels, with consequences that compound across generations. Shielding can reduce but not eliminate this hazard. Dense materials absorb or deflect lower energy particles. Water, polyethylene, and certain metals provide varying degrees of protection against different components of the radiation environment. A crew habitat surrounded by thick layers of water or polyethylene would be meaningfully better shielded than an unprotected vessel. But there are two fundamental limitations that no shielding strategy can overcome. The first is mass. Effective radiation shielding is heavy. Adding sufficient shielding to meaningfully reduce cosmic ray exposure over a journey of decades requires adding substantial mass to the vessel. This mass must be accelerated along with everything else, which multiplies the energy requirements, which compounds the propulsion problem that is already at the limits of conceivability. Every kilogram of shielding added is a kilogram that demands its own propulsion energy, which demands its own fuel mass, which demands its own propulsion energy. The feedback is the same tyrannical loop that governs all aspects of interstellar propulsion. The second limitation is more fundamental. High-energy cosmic rays cannot be stopped by any practical thickness of any known material. These particles, primarily protons and heavier nuclei, accelerated to near light speed by the most violent processes in the universe: supernova remnants, neutron star mergers, jets from active galactic nuclei, carry energies so extreme that they pass through meters of solid lead with only modest attenuation. The most energetic cosmic rays ever detected carry kinetic energies comparable to a tennis ball thrown at moderate speed, concentrated into a single subatomic particle. A spacecraft surrounded by meters of solid metal would still pass through the interior of the crew habitat for every one of these ultra-high energy particles that happen to be traveling in the right direction. In practice, most cosmic rays are not at their theoretical maximum energies. The flux that penetrates a well-shielded habitat would be lower than an unshielded vessel, but the flux cannot be reduced to zero. Over decades and centuries of exposure, the residual cosmic ray penetration delivers biological damage that accumulates without recovery, degrading the health of crew members in ways that no medical intervention aboard the ship can fully address because the underlying cause, the radiation itself, cannot be removed. There is another hazard at relativistic speeds that operates at a scale between individual particle impacts and the continuous flux of background radiation: micrometeoroids. Interstellar space is not entirely free of larger solid particles. Cometary debris fragments from ancient collisions and material ejected from stellar systems over billions of years has seeded the interstellar medium with objects ranging from microscopic grains to particles a millimeter or more in diameter. At 10% of light speed, a 1 millimeter particle, something roughly the size of a grain of coarse sand, carries kinetic energy equivalent to several tons of TNT. A 1 centimeter particle, a pebble by everyday standards, carries energy equivalent to a nuclear weapon. The probability of encountering any specific particle in a given volume of interstellar space is low, but over a journey spanning light years, a spacecraft sweeps through an enormous volume of space. The accumulated probability of encountering a particle large enough to cause catastrophic damage is not negligible. It is not something that can be dismissed as astronomically unlikely, in the way that truly rare events can be dismissed. It is a genuine engineering constraint that demands either active deflection systems, which consume energy and add complexity, or passive shielding thick enough to absorb the impact of a particle carrying multi-ton TNT equivalent energy, which adds mass and feeds back into the propulsion. Problem: active deflection using electromagnetic fields can deflect charged particles, which addresses much of the ion and proton flux from the interstellar medium. But neutral particles, dust grains that carry no electric charge, are immune to electromagnetic deflection. They must be stopped physically. A physical shield capable of stopping a 1 centimeter particle traveling at 10% of light speed would need to be extraordinarily thick and dense, adding a mass burden to the ship that approaches or exceeds the mass of the rest of the vessel. The engineering of interstellar protection is not a problem with a clean solution. Every approach trades one set of constraints for another. Electromagnetic deflection addresses charged particles but ignores neutral ones. Physical shielding stops neutral particles but adds prohibitive mass. Maneuvering to avoid hazards requires continuous sensing and reaction systems that consume power and add mechanical complexity. And all of these systems must function without failure for the entire duration of the journey across decades or centuries, maintained by a crew or their descendants, using only the resources available within the ship. Navigation at interstellar distances introduces its own category of hazard that operates not through physical impact, but through the mathematics of precision. To travel from one star to another, a spacecraft must maintain a trajectory accurate enough that it actually arrives at its destination rather than sailing past into empty space. This sounds straightforward. In practice, it requires a degree of navigational precision that has no precedent in human engineering. Consider the geometry. A spacecraft departing the solar system aimed at a star 4 light-years away must maintain a trajectory accurate to within a fraction of the star's diameter across a distance of 25 trillion miles. The angular precision required is comparable to shooting a bullet from one city and hitting a specific coin lying on the sidewalk in another city thousands of miles away. A navigational error of 1/10,000th of a degree at departure translates into a positional error of billions of miles at the destination. In the vacuum of interstellar space, there is no medium to resist small deviations in trajectory. There is no GPS network to provide position fixes. There is no ground control that can send timely corrections because any message from Earth takes years to arrive and any response to that message takes years more. The spacecraft must navigate autonomously using only the instrumentation it carries, correcting its course through observations of stellar positions that shift imperceptibly over the years of the journey. Minor course corrections require thrust. Thrust requires fuel. Fuel was already fully allocated at departure. Any course correction mid-journey comes at the cost of either final velocity or deceleration capacity at the destination, both of which were calculated to their minimum viable levels. The navigational margin built into an interstellar mission is necessarily thin, and the stars themselves are not stationary. They move relative to each other at velocities of tens of kilometers per second. A mission launched toward a star's current position will not arrive where the star is now. It must be aimed at where the star will be in 40 years, or 100 years, or 1,000 years. A calculation that requires knowing the star's proper motion with precision across the entire duration of the journey. Precision that requires observations extending over decades or centuries. Observations that may contain small systematic errors that accumulate into significant positional uncertainties by the time the ship arrives. All of this, the particle bombardment, the radiation damage, the micrometeoroid hazard, the navigational precision, exists simultaneously, each problem compounding the others, each solution to one problem creating new constraints for the others. The ship that must be heavily shielded against radiation is heavier and harder to navigate precisely. The ship that must carry maneuvering fuel for course corrections has less fuel available for deceleration. The ship that is built robustly enough to survive micrometeoroid impacts is heavier and requires more propulsion energy. The ship that carries a large population for genetic viability is larger and heavier and requires more shielding and more fuel and more manufacturing capacity for repairs. The interstellar medium is not a neutral background through which a spacecraft glides. It is an environment that actively degrades everything the spacecraft is made of, that poses genuine lethal hazards to anything biological aboard, and that demands engineering responses to each hazard that compound the engineering requirements of every other hazard. There is no configuration of mass shielding propulsion and crew size that simultaneously satisfies all of these constraints at levels that would allow a mission to succeed across the timescales interstellar travel requires. This is what the void actually is, not empty space, not a peaceful darkness between the stars, a slow-motion disassembly process that takes apart everything passing through it atom by atom, cell by cell, year by year, millennium by millennium. It does not move. It does not chase the traveler. It simply surrounds them, permeates them, and waits for the accumulation of small damages to exceed the capacity of any system to repair itself. Even if they exist, the universe itself prevents them from getting here. Distance establishes the scale of the problem. Energy establishes the cost of attempting it. Time establishes the duration across which every other challenge must be sustained. And the void itself, the radiation, the particles, the navigational demands, the slow entropic erosion of every material and biological system establishes that even a mission that has solved for distance and energy and time still faces an environment that works continuously and relentlessly against its survival. Each of these barriers stands independently. Each one confronted in isolation would represent a challenge of civilization scale magnitude. Together, they do not merely add, they multiply, they interact. They create a system of constraints in which solving one tightens another, in which every engineering response to one hazard generates new burdens for the others, in which the total challenge exceeds the sum of its parts by a margin that grows with every honest attempt to quantify it. And there is still one more dimension of this problem that has not yet been addressed. because someone will always arrive at this point and say that all of the above assumes human technology, human limitations, human timescales. Someone will always say that a civilization sufficiently advanced would find solutions we cannot currently conceive. That the barriers described here are barriers of ignorance, not of physics. That given enough time and enough intelligence, every wall falls. This argument deserves a direct and careful response. Not because it is obviously wrong, but because it contains a subtle confusion between what technology can change and what the laws of the universe prohibit. And that distinction is the difference between a solvable engineering problem and a permanent feature of reality. That is where we go next. There is a response to everything discussed so far that arrives with the confidence of common sense. It surfaces in comment sections and late-night conversations and the margins of books about the Fermi paradox. It presents itself as the voice of humility and open-mindedness, as the reasonable corrective to the arrogance of assuming that human limitations define universal ones. It goes like this: you are thinking too small. You are projecting the constraints of a primitive, newly technological species onto civilizations that may have existed for millions of years before our sun ignited. You are assuming that the barriers described here, the distance, the energy, the time, the radiation, are permanent features of reality, rather than temporary obstacles awaiting solutions that a sufficiently advanced intelligence will eventually to discover. Every barrier humanity has ever faced looked insurmountable until it was surmounted. The Atlantic Ocean looked uncrossable until it was crossed. The sound barrier looked absolute until it was broken. The moon looked unreachable until we stood on it. Why should the barriers to interstellar travel be different? This argument feels powerful because it appeals to a genuine pattern in human history. Technological progress has repeatedly demolished what appeared to be fundamental limits. It weaponizes humility, suggesting that anyone who accepts the barriers described here is simply lacking imagination, is failing to think at the scale that the question demands. But the argument contains a confusion so fundamental that it undermines itself completely. And understanding this confusion is essential to understanding why the barriers described in this story are not barriers of ignorance waiting for sufficiently clever engineering. They are barriers of physics. And physics is not a wall that intelligence eventually scales. It is the floor beneath every wall, the ground that every civilization in this cosmos stands on, regardless of how long they have been standing. The confusion is this: the argument treats all barriers as equivalent. It assumes that because some barriers have yielded to technology, all barriers will yield to technology. But this assumption ignores a critical distinction between two fundamentally different kinds of barriers. There are barriers of engineering, which are limitations imposed by current knowledge and current capability limitations that can in principle be overcome as knowledge and capability advance. And there are barriers of physics, which are limitations imposed by the structure of reality itself, limitations that apply to every process in the universe, regardless of who is doing the engineering or how sophisticated their technology has become. The sound barrier was a barrier of engineering. There was no law of physics forbidding travel faster than sound. The barrier existed because the aerodynamic understanding and materials science of the early 20th century had not yet reached the level required to build aircraft that could manage the shock waves and structural stresses of transonic flight. Once the understanding and the materials advanced sufficiently, the barrier fell. It was never a feature of reality. It was a feature of ignorance. The speed of light is not a barrier of engineering. It is not a limitation imposed by insufficient knowledge or inadequate materials. It is a structural property of space-time, woven into the geometric relationship between space and time that Einstein's special relativity describes, and that every experiment ever designed to test it has confirmed. The speed of light as an absolute limit is not a provisional hypothesis awaiting revision. It is one of the most thoroughly verified facts in the history of science, confirmed by particle accelerators, by atomic clocks, by the behavior of GPS satellites, by the spectral shifts of light from distant galaxies, by the timing of pulsar signals, by more than a century of increasingly precise measurement across every relevant domain of physics. The speed of light cannot be exceeded by any object with mass, not because no one has yet built a fast enough engine, because exceeding light speed would require supplying infinite energy to a massive object, and infinity is not an engineering target. It is a mathematical absolute. As any massive object accelerates toward light speed, the energy required to accelerate it further does not merely increase. It approaches infinity asymptotically. You can add more energy. You can always add more energy, and the object will always remain below light speed, getting closer, with each increment never arriving because the destination is not a finite point on a curve, but the limit toward which the curve extends without ever reaching. This is not a human limitation. It is a property of how spacetime functions. It applies to silicon-based life, carbon-based life, digital consciousness, energy beings, and every other form of intelligence that occupies physical space and manipulates physical matter. The universe wrote this rule before any civilization existed to read it. Begin with the most structured version of the advanced civilization argument. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale for classifying civilizations by their total energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the 16th watts, for an Earth-sized world. A Type 2 civilization harnesses the entire output of its host star, roughly 4 times 10 to the 26th watts, for a Sun-like star. A Type 3 civilization harnesses the energy output of its entire galaxy, roughly 4 times 10 to the 36th watts for a Milky Way scale system. Humanity currently sits at approximately 0.7 on this scale. We capture a fraction of the energy that reaches Earth from the Sun. We have not yet approached the theoretical maximum of our planetary energy budget, let alone the output of the star that generates it. The Kardashev scale is frequently invoked to suggest that a sufficiently advanced civilization would find interstellar travel energetically trivial. A Type 2 civilization commanding the full power of its star should be able to launch starships the way we launch satellites, the argument goes. The energy wall would crumble before such staggering power. But this reasoning confuses the total energy available with the energy required for a specific task. A Type 2 civilization can generate the energy more easily than we can. They can afford the fuel bill more comfortably, but they cannot pay a smaller bill. The bill is set by physics, not by economics. The minimum kinetic energy required to accelerate a given mass to a given velocity is fixed by the relationship between mass velocity and the speed of light. No amount of available power reduces this minimum. The floor is set by the universe. Technology determines only how efficiently a civilization can approach that floor, never how far below it they can go. Consider a direct analogy. Lifting a 1 kilogram object 1 meter against Earth's gravity requires approximately 10 joules. This is true whether the lifting is done by a human hand, a simple pulley, or a precision robotic arm, designed by the most advanced engineers imaginable. The mechanism changes. The energy requirement does not. You can lift more efficiently, losing less energy to friction and heat, but you cannot lift for less than 10 joules, because 10 joules is what the gravitational field and the mass require, and neither the gravitational field nor the mass are altered by the sophistication of the machine. The same principle governs interstellar propulsion absolutely and without exception. A Type 2 civilization commanding the full output of a star could generate the energy needed to accelerate a large interstellar vessel to a significant fraction of light speed in a fraction of a second rather than decades. That is a genuine advantage. But the total energy expenditure remains fixed by the mass and the velocity. It does not shrink, it does not become negligible. It remains a real cost imposed by real physics paid from a larger but still finite budget. And launching a fleet of such vessels, the kind of systematic program of interstellar exploration that would be required to visit Earth from a distant star system, would consume a measurable and significant fraction of even a stellar energy budget. More energy does not change the speed limit. It does not compress the distance between stars. It does not stop the clock aboard a ship in transit. It does not eliminate radiation damage, or social fragmentation, or mechanical entropy. It simply means the civilization can write a larger check. The check itself, its minimum value, remains determined by physics. Now, address the proposals that claim not to overpower the physical barriers, but to circumvent them entirely. The warp drive concept most formally articulated by physicist Miguel Alcubierre in a 1994 paper published in the journal Classical and Quantum Gravity proposes a method of faster-than-light travel that does not require any object to exceed light speed through its local space. Instead, the idea involves contracting the fabric of spacetime in front of a vessel and expanding it behind, creating a bubble of warped spacetime that carries the ship along faster than light without the ship itself moving faster than light relative to its immediate surroundings. The mathematics within the framework of general relativity are internally consistent. The concept does not obviously violate the specific prohibition against massive objects exceeding light speed locally. The physics, however, are categorically devastating. An Alcubierre drive requires a substance with negative energy density to create and sustain the warp bubble. Negative energy density means matter that weighs less than nothing that gravitationally repels rather than attracts, that has properties diametrically opposite to every form of matter and energy ever observed in nature. No such material has been detected in any experiment. No theoretical framework within established physics produces it in quantities sufficient to be useful. The existence of macroscopic quantities of negative energy density matter may be fundamentally prohibited by the same laws of quantum field theory that describe every other aspect of particle physics with extraordinary precision. In Alcubierre's original calculation, the energy required to create the warp bubble was of order the total mass energy of the observable universe. Later theoretical refinements by Harold White and others suggested that certain geometric configurations might reduce this requirement. But even the most optimistic of these refinements still requires exotic matter with negative energy density in quantities that have never been produced, never been observed, and may not be physically possible. And every refinement that reduces the energy requirement simultaneously introduces new theoretical problems, including violations of energy conditions that general relativity requires for causally stable spacetimes. The Alcubierre drive is a mathematical curiosity, a demonstration that general relativity's equations permit certain exotic solutions when you input parameters describing matter that does not exist. Calling it a blueprint for engineering is like calling the solution to an equation that requires the square root of a negative number a blueprint for counting physical objects. The mathematics work internally. The physical requirements are absent from the universe. Wormholes present an identical class of problem, an Einstein-Rosen bridge. The formal name for what popular culture calls a wormhole is a theoretical topological feature of spacetime that would connect two distant regions through a tunnel-like shortcut. If stable, traversable wormholes existed, they would allow travel between distant points in times far shorter than the light travel time between those points. They represent the most physically grounded of the proposed faster-than-light solutions in the sense that they emerge from the mathematics of general relativity rather than from speculation beyond it. But every solution to Einstein's field equations that produces a traversable wormhole requires to hold the throat of the wormhole open against its natural tendency to collapse precisely the same exotic matter with negative energy density that the Alcubierre drive demands. Without this exotic matter, a wormhole collapses faster than any object could pass through it. The collapse occurs at the speed of light. You cannot outrun it, because you cannot travel at light speed. Additionally, traversable wormholes would almost certainly violate causality. If you can travel instantaneously between 2 points separated in space, special relativity's treatment of simultaneity, which varies for observers in relative motion, implies that you can in principle arrive at your destination before you departed from your origin. This creates closed time-like curves paths through space-time that loop back on themselves, which most physicists regard as physically prohibited. Stephen Hawking formalized this intuition as the chronology protection conjecture, the hypothesis that the laws of physics conspire to prevent the formation of closed time-like curves because the alternative creates logical paradoxes that a consistent universe cannot accommodate. Wormholes are not engineering challenges awaiting better materials and more advanced construction techniques. They require matter that does not exist, and they may be prohibited by the same causal structure of spacetime that makes the universe logically consistent. There is a class of proposals that accepts the impossibility of faster-than-light travel, and instead asks whether the barriers to sublight interstellar travel might be circumvented through automation and self-replication, rather than crewed missions. The most sophisticated version of this idea is the von Neumann probe, named after mathematician John von Neumann, who first formally analyzed the concept of self-reproducing machines in the 1940s and 1950s. The concept is elegant. Instead of sending a crewed vessel across the void at enormous energy cost, a civilization sends a single robotic probe to a nearby star. The probe is designed not merely to observe and report, but to manufacture. Upon arrival, it uses the raw materials of the target star system, asteroids, comets, planetary surfaces, to construct copies of itself. These copies travel to the next nearest stars, replicate again, and spread outward in an expanding wave. Each generation doubles the number of probes. Even at modest velocities, a von Neumann wave could theoretically spread across the entire Milky Way in a few million years, mapping every star system, observing every planet, reporting every civilization it encountered. This concept deserves serious engagement because it is the strongest argument for the feasibility of interstellar exploration, the one that most plausibly circumvents the energy and time barriers by eliminating the need for crewed missions and reducing the energy cost per mission to something approaching the minimum required for a small automated vehicle. And even this concept fails under scrutiny, not because the idea is unphysical in principle, but because the implementation requirements are so demanding that the concept collapses when examined at the level of actual engineering and actual physics rather than mathematical abstraction. Self-replication at the level required for a von Neumann probe is not three-dimensional printing. It is autonomous molecular-scale manufacturing of extraordinary complexity, performed in alien environments using resources that differ from star system to star system in ways that cannot be fully anticipated at the point of design. The probe must mine raw materials from asteroids or planetary bodies whose exact composition is unknown until arrival. It must refine those materials into usable components with purity levels sufficient for precision manufacturing. It must assemble exact copies of itself, including every sensor, every processor, every line of its own software, every component of its propulsion system, from materials whose properties may differ subtly from those used in the original design. Each replication cycle introduces errors. No copying process is perfect at any scale. Each generation of probes will contain small deviations from the original design. Most of these deviations will be harmless. Some will degrade probe function. Some will degrade replication fidelity, meaning the next generation will contain even more errors. Over thousands of generations spanning millions of years, the accumulated copying errors transform the probe population into something increasingly distant from the original design, subject to the same evolutionary pressures that govern biological organisms drifting in unpredictable directions, shaped by which variants happen to replicate successfully in their particular star system environments. Natural selection might preserve functional probes and eliminate broken ones, but natural selection in this context is not guided by the goals of the civilization that launched the original probe. It is guided by reproductive success in whatever environment the probe finds itself. A probe variant that replicates more efficiently but reports less accurately would outcompete a probe that maintains reporting fidelity at the cost of replication speed. A probe that strips asteroids efficiently in metal-rich systems would proliferate in those systems, while variants optimized for different resource profiles would dominate elsewhere. The wave of probes spreading across the galaxy would evolve, diverge, and specialize in ways that the originating civilization could neither predict nor control. After millions of years and thousands of generations, the probes filling the galaxy might bear only a distant mathematical relationship to their ancestors. Their behavior, their goals, their communication protocols, their understanding of their own purpose all of it would have drifted beyond any meaningful connection to the civilization that launched the first one. They would be, in the most literal sense, alien. Communication with the home civilization would fail long before this point. A probe in a star system 10,000 light-years from its origin sends a signal home. That signal takes 10,000 years to arrive. The civilization that launched the original probe is 10,000 years older, assuming it still exists. The signal it receives describes a star system whose current state is 10,000 years removed from what the probe observed. The response, if one is sent, takes another 10,000 years to arrive. The exchange of information is not a conversation. It is the exchange of historical records between civilizations separated by vast gulfs of time as well as space. Even the most optimistic scenario for von Neumann probes, one in which self-replication works perfectly, copying errors are negligible, and communication links are maintained across galactic distances, still requires millions of years for the wave to spread across the galaxy. The civilization that launched the probes will not exist in any recognizable form when the wave reaches distant star systems. The mission will be complete, in some technical sense, the galaxy mapped, the civilizations catalogued, but the entity that benefits from this knowledge will be so different from the entity that initiated the mission that the connection between them is philosophical rather than practical. Even if they exist, the universe itself prevents them from getting here. There is one more dimension of the advanced civilization argument that is almost never addressed directly, perhaps because it requires confronting something uncomfortable about the nature of civilizations themselves. The argument assumes that advanced civilizations persist, that they grow in capability across timescales long enough to develop and deploy interstellar technology, that the window of technological capability, the period during which a civilization possesses the means to attempt interstellar travel, is long enough to result in actual missions. There is no evidence that this assumption is correct. Humanity has been a technological civilization in the modern sense, capable of generating and directing large quantities of energy in controlled ways for roughly 250 years. We have been a spacefaring civilization for less than 70 years. The window during which we have possessed any interstellar capability today whatsoever, which we do not yet meaningfully possess, is measured in decades. Against the backdrop of geological time, against the 4.5 billion years of Earth's existence, against the 13 billion years of the galaxy's history. Our technological window is a flash so brief that statistical analysis of its duration provides essentially no information about how long such windows typically last. Civilizations face internal pressures that technology does not automatically resolve. Resource depletion, climate change, political fragmentation, ideological conflict, pandemic disease, the development of technologies that are destructive faster than the development of technologies that are constructive. The arc of a civilization's development is not guaranteed to be an ascending curve toward greater capability and interstellar reach. It may be a curve that rises plateaus and declines within a window so narrow that interstellar travel is never achieved before the window closes. If the window of interstellar capability for a typical civilization is 1,000 years, then a galaxy populated by civilizations distributed across billions of years of stellar history would at any given moment contain mostly civilizations that have either not yet developed the capability or have already passed through the window and declined. The overlap between civilizations capable of interstellar travel existing at the same time within communication range of each other pointed toward the same destination is not merely small. It may be effectively zero. The galaxy might be full of ruins. Civilizations that rose reached toward the stars and collapsed before the first ship completed its journey. Archaeological records in the geology of dead worlds. Radio emissions from societies that fell silent before their signals crossed the distances separating them from their nearest neighbors. The cosmos may be less a community of advanced civilizations sharing knowledge across the stellar network, and more a succession of isolated experiments, each one burning briefly, reaching tentatively outward, and extinguishing before making contact. This is not pessimism. It is a sober reading of the one data point available, the history of Earth's own civilization, extended by the principles of physics and statistics across the broader galactic context. The barriers are real, the windows are short, the distances are vast, and the universe, indifferent to the aspirations of any particular species on any particular world, does not adjust its constants to accommodate the desire for connection. Even if they exist, the universe itself prevents them from getting here. Every proposed solution to the interstellar travel problem, faster than light, drives wormholes, generation ships, von Neumann probes, relativistic time dilation, Kardashev scale energy budgets, runs into the same wall from different direction. The wall is not made of human ignorance. It is made of the speed of light, the conservation of energy, the second law of thermodynamics, the behavior of matter under extreme radiation, the dynamics of isolated human communities across geological timescales, and the brevity of civilizational windows against the depth of cosmic time. These are not problems that a smarter civilization solves. They are the conditions under which every civilization operates, regardless of intelligence, regardless of age, regardless of accumulated knowledge. The universe issued these conditions at its beginning and has not revised them since. They will not be revised. They are not subject to revision by any process within the universe, because they are the process within which every process in the universe occurs. The night sky is beautiful. The stars are real. The civilizations that may orbit them are, for all we know, genuine, intelligent, curious, and reaching toward us across the same void that separates us from them. But between here and there, between any 2 points in this cosmos where minds have arisen to wonder about each other, the universe has placed a barrier that no mind has ever crossed, and that the laws of physics suggest no mind ever will. Not because the minds are insufficient, because the universe is too large, too slow, and too indifferent to the connections its inhabitants long to make. Even if they exist, the universe itself prevents them from getting here. There is only one dimension of this story that remains, not a technical dimension, not a dimension of physics or engineering or mathematics, a dimension that these numbers and equations taken together ultimately open onto. Because when you have followed the logic of interstellar impossibility all the way to its conclusion, when you have sat with everything that the distance and the energy and the time and the void and the limits of physics collectively mean, you arrive somewhere unexpected. You arrive not at despair, but at something quieter and stranger, and more important. That is where we go next, and it is where this journey ends. Come back to the beginning. Come back to that clear night, to the stars scattered across the dark above you, to the ancient and persistent illusion that they are close. You have traveled a long way since then, not in distance, but in understanding. You have followed the mathematics of interstellar space, from the deceptive beauty of the night sky, down through layers of physical reality that most people never examine, through the arithmetic of light years and the brutality of the rocket, to the equation, through the slow erosion of time and the lethal patience of the void, through the theoretical proposals that promise shortcuts and the physical laws that close every door those proposals attempt to open. You know now what the night sky conceals. The nearest star is 25 trillion miles away, a distance so absolute that our fastest spacecraft, launched nearly 50 years ago and flying without pause ever since, has covered less than one light day of the 4.24 light years that separate us from it. At its current speed, that spacecraft requires 73,000 years to complete the crossing. The galaxy that contains both our Sun and every other star visible to the naked eye stretches 100,000 light years from edge to edge, a span so vast that light itself, traveling at 670 million miles per hour, needs 100,000 years to cross it. The observable universe extends 93 billion light years in every direction, containing an estimated 2 trillion galaxies, each one an island of hundreds of billions of stars separated from the next by distances that make the Milky Way's interior seem intimate by comparison. These numbers are not approximations. They are not dramatic embellishments chosen for effect. They are measurements confirmed by multiple independent methods across more than a century of increasingly precise astronomical observation, and they describe a cosmos built at a scale that renders the concept of interstellar travel not merely difficult but structurally, fundamentally, and in all likelihood permanently beyond the reach of any civilization constrained by the physics of this universe. The energy required to accelerate even a modest spacecraft to a meaningful fraction of light speed exceeds the annual energy output of our entire civilization by orders of magnitude. The time required to cross interstellar distances at achievable velocities exceeds the lifespan of every institution humanity has ever built. The radiation environment of the interstellar medium erodes every material and every biological system it touches, without pause, without mercy, without any mechanism that engineering can fully arrest. Every proposed shortcut, every theoretical framework that promises to circumvent the speed of light or compress the distances between stars requires matter that does not exist, or energy that cannot be produced, or violations of the causal, the structure of space-time that would unravel the logical consistency of the universe itself. This is not a conclusion that human civilization has arrived at through ignorance or pessimism or failure of imagination. It is a conclusion that follows directly and inevitably from the most thoroughly tested theories in the history of science, applied honestly to the actual distances between actual stars in an actual galaxy whose dimensions have measured with extraordinary precision. The universe is not hostile to life. It is not hostile to intelligence. It is not hostile to the desire for connection that arises, it seems, wherever minds capable of looking upward manage to exist. It is simply indifferent to these things. It built itself according to rules that predate any civilization and that will outlast every civilization. And those rules taken together produce a cosmos in which the light travel time between neighboring stars is measured in years. The energy cost of crossing that gap is measured in civilizational budgets, and the passage of time during the crossing is measured in generations and centuries and millennia. The silence of the cosmos does not mean we are alone. This is perhaps the most important single thought to carry away from everything explored in this journey. The Fermi paradox, the famous question attributed to physicist Enrico Fermi, who allegedly asked over lunch in 1950, "Where is?" Everybody is often treated as evidence that intelligent life must be rare. If the galaxy is old enough and large enough to have produced countless civilizations, the reasoning goes, then surely some of them should have reached us by now. The absence of confirmed contact becomes in this framing evidence of absence. We do not hear from them because they are not there. But this reasoning contains a hidden assumption that the physics examined here exposes as unfounded. It assumes that a sufficiently advanced civilization would have reached us. It assumes that the barriers to interstellar travel are barriers of technology rather than physics temporary obstacles that any civilization with enough time would eventually overcome. It assumes that the silence is surprising, that the default expectation should be contact rather than isolation. The physics says otherwise. The physics says that the silence is exactly what we should expect. It says that the default state of any cosmos built with these particular constants, this particular speed of light, these particular relationships between mass and energy and velocity, is isolation, not hostile isolation. Not the isolation of a prison or a quarantine, the isolation of an archipelago, of islands scattered across an ocean so wide that no ship built from the materials available on any island can cross it in the lifetime of the civilization that builds the ship. The silence is not evidence that we are alone. It is evidence that the cosmos is very, very large, and that the rules it operates by enforce a separation between its inhabitants that no amount of intelligence or ambition or technological sophistication can fully bridge. The universe may be saturated with minds. Every spiral arm of every galaxy may harbor civilizations that have looked upward and wondered and reached for answers with the same hunger that drives human science and human exploration. And every one of those civilizations sits inside its own bubble of isolation, surrounded by the same distances, subject to the same physical laws, facing the same impossible arithmetic. They cannot reach us. We cannot reach them, not because either party is insufficient, because the universe between us is too large and too slow and too governed by rules that apply without exemption to everything that exists within it. There is a grief in this if you let yourself feel it. The grief of a species that looked up at 10,000 visible stars and felt kinship with the possibility of minds behind those points of light, and then did the mathematics and understood that the kinship is real, but the contact is impossible. That the universe is full of questions that will never receive answers because the questions and the answers are separated by distances that light itself takes centuries to cross. That there are, in all probability, civilizations in this galaxy right now that are looking at a sky that contains our sun and wondering the same things we wonder when we look at their sky, and that we will never know what they concluded, and they will never. I know what we concluded because the messages we might send to each other will not arrive for hundreds or thousands of years, and the civilizations that sent them may not survive long enough to receive a reply. This is a real grief. It deserves acknowledgement before it is set aside. But set it aside and something else comes into focus. Something that the scale of cosmic isolation understood fully and honestly makes more visible rather than less. We are here, not as an abstraction, not as a statistical entry in an equation about the probability of life in the universe, as a concrete, specific, improbable fact. On one small, rocky world orbiting one unremarkable yellow star in the outer suburbs of one ordinary spiral galaxy among 2 trillion, something happened. Complex chemistry organized itself into biology. Biology organized itself into nervous systems. Nervous systems organized themselves into consciousness. Consciousness organized itself into language, mathematics, science, philosophy, music, and the capacity to look outward at the cosmos and ask what it is and how it works and whether anyone else is looking back. This did not have to happen. There is nothing in the laws of physics that required it. The universe ran for 9 billion years before Earth formed, and for another 4.5 billion years after Earth formed before anything on its surface was capable of measuring the distance to the nearest star. For most of cosmic history, the universe was a place in which the distances between stars existed, but no mind was present to be troubled by them. The silence was not experienced as silence because there was no one to hear it. Now there is. The fact that you are here, that you have followed this journey through the mathematics of interstellar impossibility and emerged on the other side still capable of feeling something about what the numbers mean, is not a small thing. It is by any honest accounting of cosmic probability an extraordinary thing, a rare convergence of physical conditions, chemical processes, evolutionary pressures and historical contingencies that produced on this particular world at this particular moment, a mind capable of measuring the universe and being awed by its own measurements. The cosmic isolation that physics enforces is real, the barriers to interstellar contact are real, the silence that results from those barriers is real. But the fact of consciousness, the fact of understanding, the fact of the capacity to ask questions about the nature of reality and to develop methods for answering them, this fact is not diminished by the scale of the cosmos that surrounds it. It is, if anything, made more remarkable by it. Consider what it means to be a creature, small enough to be invisible from the nearest star, living on a rock that would fit inside our own sun, more than 1 million times orbiting a star that is one of 400 billion in a galaxy that is one of 2 trillion in an observable universe, 93 billion light-years across, and to nonetheless possess the capacity to measure all of this. To determine the distance to Proxima Centauri using the parallax shift of its position against background stars as Earth moves around the Sun. To calculate the size of the observable universe from the redshift of light from distant galaxies. To derive the energy requirements for relativistic acceleration from first principles of mechanics and electromagnetism. To understand with genuine precision why the stars that appear close on a clear night are in fact separated by voids so vast that no physical object has ever crossed them. This is what science is, not merely the accumulation of facts about a universe indifferent to the beings it contains, but the improbable, repeated, astonishing act of small creatures in a large cosmos reaching out with mathematics and measurement and finding that reality answers back. Finding that the universe, though it does not care about us, is nonetheless comprehensible to us. That the rules it operates by are not arbitrary or opaque, but structured and consistent and with sufficient effort Discoverable. The barriers to interstellar travel are real. They will likely never be crossed in any form resembling the journeys imagined in science fiction. The alien civilizations that may exist in this galaxy are in all probability as permanently separated from us as we are from them, each one burning briefly on its own small world, surrounded by distances it cannot cross, looking upward at a sky that holds no visitors and sends no messages that will arrive in time to matter. But the looking itself matters. Every civilization that has ever looked upward and asked what is out there, whether in this galaxy or any other, has performed the same fundamental act. The act of refusing to accept the darkness as simple darkness. The act of insisting that the points of light mean something, and that meaning can be found by looking carefully and thinking rigorously and following the evidence wherever it leads, even when it leads to conclusions that are humbling, strange, and difficult to hold. We performed this act. We looked at the night sky, which lied to us about the distances, and we refused to accept the lie. We measured. We calculated. We built instruments of extraordinary sensitivity and aimed them at stars so far away that the light reaching us left those stars before humans existed. And from that ancient light, we extracted the truth about where those stars actually are and how far they actually sit from our small world. We found that they are unreachable, and we understood precisely why. And that understanding, that precise, honest, mathematically grounded understanding of the scale and structure of the universe we inhabit, is one of the most remarkable things that has ever happened in this cosmos. Perhaps in any cosmos. The stars will not come to us. We will almost certainly not reach them. The silence between worlds is not a problem awaiting a solution. It is the architecture of reality built into the universe at its foundation, enforced by laws that predate every civilization and will outlast every civilization and apply to every mind that has ever arisen in every corner of this extraordinary and indifferent cosmos. But here on this world, in this brief window of time, something looks out at that silence and understands it. Something small enough to be invisible from the nearest star has measured the distance to that star and knows with precision that would have seemed miraculous to any previous generation of humans exactly how far away it is and exactly why. It cannot be crossed. That is not nothing. That is in a universe of 2 trillion galaxies and 400 billion stars per galaxy, and distances measured in units that take years, just to name almost incomprehensibly rare. The candle flames burn in the cathedral, each one small, each one temporary, each one surrounded by a darkness that stretches farther than light has traveled since the beginning of time. They do not touch each other. They cannot. The darkness between them is too vast, and the physics too absolute, and the windows of their burning too brief against the depth of the night. But they burn, and the light they cast, however small, however local, however utterly lost against the scale of what surrounds it, is real. It illuminates something. It warms something. It makes visible for the duration of its burning a small circle of what would otherwise be absolute dark. We are one of those flames. We burn in a cathedral we cannot cross. We light a circle of understanding in a cosmos that did not require our understanding and will not mourn its absence when we are gone. We have measured the darkness and found it incomprehensible in its scale and perfect in its indifference, and ours, entirely ours, for as long as this small fire holds. The warmth is here, on this world, in this moment. It is extraordinary. It is temporary. And it is ours.